how I'm able to navigate these tabs is beyond me. Hello everyone, today we're going to be trying to add features to our recurrent neural network to make it train faster. So we're specifically going to be adding momentum and Nesterov momentum update to our network. What I really love about this, is it graphic or animation I'll call it, is this kind of just highlights the benefit of using different update methods. So SGD here is vanilla update, which is what we currently have. What we're going to be implementing today is momentum and Nesterov momentum. I could implement these, but frankly I don't understand them, so we're just going to ignore those. We've already gone ahead, we've already implemented that in our Excel. So what I will be doing is I will just be, again, just copying what we've already done, translating it into code. In order to implement momentum, we're just going to need a variable called v. V tries to use, again, physics, so properties of physics. It'll take a look at, where's the steepest slope, and where can I pick up the most speed going down the slope. If we go back to our graphic, that's exactly what happens, right? What happens is once, again, the green and the purple, once momentum, these different momentum updates, once they find a good enough slope, and they're able to determine it, they just shoot right down it. If you roll a ball down the hill, it'll just keep gaining speed. It'll get faster and faster as it's rolling down the hill. So, or actually, I already have this implemented in my main neural network library. So let me see if I can just go ahead and just copy that. Why duplicate efforts? Because it's not really too complex, right? You just implement the formula that's already laid out for momentum update, and that's that. So you're just taking a new hyperparameter called mu. You're multiplying it by the variable v. So for the first instance or the first epoch, v is 0, and then you're just subtracting the learning rate times the weights or the deltas that we got, and then you just add it to your weights, and that's how you update the weight. So rather than just doing this, which we would normally do, you're just adding this. The mu times v. Okay, so as we're implementing v, one thing we need to keep in mind is we need a v for each set of weights. So we need an e for our weights 1, our weights 2, our weights 3, our bias 1, and our bias 2. So update v during training. Okay, so now this is where we're going to implement this formula here, WHX. So let's just zoom through this. So all I'm doing is I'm getting mu, multiplying it by the old value of WHX, or at least the WHX inside this v variable, plus the learning rate times gradient. Then our new weights are, again, according to the formula. So now that we've calculated v, it's just x, so the old weight plus v, which is our momentum variable. Should be it. Again, it's not really too difficult. Let's try it out. Let's see if our network trains. Yeah, no, that's not training at all because the loss is just staying the same. Oh. What is wrong with me sometimes? I have to add the momentum to the old weights, not just set the old weights to the momentum variable. And boom. And so what's crazy is, let me actually slow this down a little bit, and we'll just see how much of a difference this makes to our training. Oh, okay. So after 50 epochs this time, momentum update was able to train and say hello in just 50 epochs, which is pretty good. Now let's change this back to vanilla update. And I think it's pretty much impossible for vanilla update to be able to train in 50 epochs. So after about like 160-ish, 170, then it's able to output hello. And the point is, and what we've determined is, momentum update is able to train and say hello within 50 epochs, whereas vanilla update, it's just not possible. There's no way it can get it done within that time. So that's just to show you how momentum update speeds up the training process. Oh man, I really need to clean up this code base. This one's quite confusing to go through. Also, I think I read a paper a while back stating that these types of update methods, they don't generalize as well as gradient descent or momentum, Nesterov momentum does, and so that's why I just generally decided to avoid them. Let's just take a look at this graphic here. I think that the performance is quite comparable. Eta delta is able to find is able to determine how to get down the slope the fastest. But if you take a look at momentum and Nesterov's momentum, so momentum is green, Nesterov's momentum is purple. They're not really that far behind the rest, right? I mean, yes, it takes them longer to find the slope, but so eta delta's already gone down. RMS prop and eta grad then go down, but they go down quite slowly. And once momentum and Nesterov's momentum, they find a slope, they just shoot down that slope really, really quickly, right? So, because of this, um, again, I don't know what to call it. I'll just call it animation. I was kind of comfortable just sticking with momentum and Nestrov's momentum, and just implementing that.